everybody. Welcome to our 10th annual Laser Fun Day. My name is Avalon McLeod.
And my name is Danny Trotz. We are the outreach chairs for the Student Optics chapter here at U of A. We are so sad that we can't host you in person this year, but we are still so excited to be able to bring the wonderful world of optics to you in this virtual platform.
Laser Fun Day today is an event that the students here at the James C. Wyant College of Optical Sciences put on every year. Today, we're going to have a fun and laser-filled day of optical demonstrations that relate to things you encounter in your everyday life.
Things like old movies, swimming pools, and even chocolate bars are all involved in optical sciences. We hope that today we can shed some light on how wonderful and widespread our field of study really is.
Just below this live stream on the laserfunday.org website, you should find a schedule of all the optical demos we're going to be doing today. There are printables, pamphlets, and even a materials list in case you want to do the demos along with us. If you are one of our younger viewers, ask your parent or guardian for help.
Our first demo today is going to be the inverted face with Miss Serena. But before we get to that, we're going to show you a quick video to introduce our college and what the study of optical sciences really is.
Thank you.
Optics is big. In the Norwood lab, we use large solar troughs to collect solar energy and turn that into electricity or purify water.
Where optics can also be small, in Dr. Seuss' Little Sensor Lab, a wide range of particle sizes with radii from 2 to 100 nanometers can be detected using ultra-sensitive microtoroid optical resonators.
Optics is near. We use microscopes to get near objects to look at things that we can't see by eye, like the surface of this 2 on the 2002 written here on this penny in our microscope. In Dr. Ewan McLeod's lab, I work on lens-free microscopes. A lens-free microscope consists of a source and a sample placed very close to the sensor. We place our sample or object very near to the sensor to collect as much light from that object as possible. We then take what we've recorded on our sensor and plug it into the computer and use code to reconstruct our object instead of lenses. Here are images of clusters of 300 nanometer spherical particles.
Optics is invisible. Although it may not look like much, we can use wavelengths of light that are invisible to the human eye to do amazing things. In Dr. Barton's lab, I design and build imaging systems that will one day be used to detect ovarian cancer.
Optics is old. We can use infrared and X-ray imaging to learn more about the origin of antique artifacts. Working with researchers in the Netherlands, I used imaging to learn the past history and authenticate Renaissance paintings.
Optics is hot. Radiological imaging uses small amounts of radioactive material in the body to image gamma rays, which are detected by a special detector in combination with collimation optics to produce functional images of a living body. By working with Dr. Fernlid, I took part in making brain imagers which detect Parkinson's and Alzheimer's disease.
Optics is fast. Using extremely short laser pulses, this cool microscope called a multiphoton microscope can diagnose diseases like cancer much faster than traditional microscope techniques. And we have a bunch of them here at the College of Optical Sciences, including in my lab. These lasers use pulses on the order of femtoseconds, or 10 to the minus 15 seconds.
Optics is far. In my time in the optics department, I've had the opportunity to work on a project that is creating the instruments to study the interstellar medium. I've also had the opportunity to work on another project that is creating a trade study to see which camera will be best to study one of Jupiter's moons, Europa.
Optics makes your dreams come true. And let me tell you how optics made my dreams come true. I joined optics because I was obsessed with space. When I was 16, I looked through that telescope and saw the rings of Saturn for the first time and knew that I needed to make space exploration a part of my life. I joined optics specifically because everything we know about space is enabled by optics technology, from telescopes which look up into space to the cameras that go on the rovers and orbiters exploring planets in our solar system. And after getting my degree in optics, I was able to get my dream job. I'm recording this from Los Angeles, where I'm working for NASA's Jet Propulsion Laboratory, which, here's the proof, my ID, there's me and there's NASA. It's an absolutely dream come true, and I share this with you because there isn't one of you watching this that could not achieve your dreams with a degree in optics. The College of Optics gives you all of the undergraduate research opportunities, internship opportunities that you would need to follow your dreams. So, join optics and make your dreams come true.
This unforgettable vacation memory, it didn't actually begin here.
All right, good. Hi, everyone. Welcome again to Laser Fun Day 2021. This will be the first demo, which is about depth perception. And my name is Sarina Grijalva. I am currently a junior here at the U of A studying optical engineering. So let's get started. So in order to talk about depth perception, I want to first talk about what it is that's actually doing the perceiving. And that would be the your eyes and your brain, along with other sensory aspects. So in this diagram that I have right here, I pointed out 4 specific features of the eye that I just want to talk about for a little bit. The first being your retina, which contains rods and cones to recognize visual information. So that's where you're getting color and sharpness. And then the choroid, which is supplying that retina with the nutrients it needs to be functioning correctly. And then the retinal veins giving oxygen to the cells. And then the good old optic nerve, which is what's actually transferring the visual information from your retina to your brain. And what's interesting about your retina is that since it's in your eye, it's this 2D structure, but it's looking out into a 3D world. So because of that fact, our brain needs to use a lot of multitude of cues to make these best informed guesses on depth, since the retina is mainly about visual information. So for your brain, the main part that's in charge of recognizing faces is what's called the fusiform area. And that area is located towards the back of your brain where the light blue section is. And we're able to find that out doing MRI scans where a person was asked to recognize a face, and then there showed an increase in blood flow in the cerebral cortex area. Again, just showing it's towards the back of the brain. So along with your visual information, your brain is ignited, and all of these are working together to give you what you understand as depth. So that brings us to the Einstein hollow face illusion. And what that is a mask of Einstein, and it doesn't have to be Einstein, it could be anybody's face, but in this case, we used Einstein. And instead of his face protruding outward like you would see a normal face, it's actually inverted, so it's like it's punched in. And the illusion is that even though it's inverted, when you're looking with the right lighting and with the right placement where you're standing, it looks like his face is actually protruding outward. So I'm going to go ahead and go to the camera and show that really quick. Okay, so here's, flip it this way, the Einstein mold that we're talking about. So this side is protruding outward, and the other side is where it's inverted, like it's punched in. So his nose is way down here.
And we'll look more at this right now. And so those cues that I was saying that your brain is making is including retinal size, relation to objects at known distances, shadows, perspective, distortion, and binocular disparity. And so as a result of all of those cues, we expect certain features of the world to behave in certain ways. And just to further explain that idea, one of the cues that's most important is the size projection of an object. So as I said, your retina is this 2D structure looking out at 3D things. So when it's seen like this arrow, this red arrow, for example, it's seeing the visual aspects of it, but not necessarily able to determine depth. So that's where, for example, size projection comes into play. So if the arrow, like the red one, is bigger, you know that the object is closer to you, or if it's smaller, you can infer that it's further away. So in summary, it's not just your visual aspects that's giving you this depth perception, but it's your visual, your brain, and then other senses like sight, hearing, smell, touch, and taste even. So I said that the Einstein face, even though it's inverted, it looks like it's protruding outward. And the reason for that is because there's two types of information that's available from viewing the hollow face. The first is contour information, and the second is depth. So from contour information, that's derived from the sharp transitions in lightness on the image, and basically just the outline of the face, of his face, and being able to make out features. And then depth information is derived from the gradual shifts in shading. And this is especially important, and I'll explain in the next slide why that is. So here we have an egg carton on the top left, and you can see it's like quote unquote inverted because that's where you're putting eggs into it. And this is just a top view of it on the top right. And so if you're shining light from above, you can tell that it still looks inverted, that you can still grab an egg and put it inside the carton. But because of the shadowing effect, when you're putting the light shining from the bottom, then it creates this shadowing that could make it look like it's protruding out towards you. So the idea is, even though it's an inverted object, the way the light is shining, it's creating shadowing that's similar to what the type of shadowing that you would see on an object that's protruding out. So if I were to shine a flashlight on my face, because of our structure, like our brows, we would get shadowing under the eyes, which is what we're seeing with this egg carton. So I'm going to go ahead and show that with the Einstein now. So here's Einstein's face. This is the side that's pointing out, and this is the inverted side. And now if I shine light from above, you can see the illusion. It looks like it's looking out towards you. And I'll go ahead and turn it around so you can see that that's actually the inverted side. And then there he is. So yeah, our brain's just kind of tricking us, but because of those cues that it's getting. So there it is. Yeah. Okay. All right. And what's also interesting, I should have shown right now, is that the eyes, not only is it appearing to protrude out, but it also, if you moved back and forth or side to side, it would look like his eyes are following you. And the reason for that, it can be explained with this slide. So if you have the top left image is, say, a mask, like a regular face that's protruding out towards you. When you're looking straight at it, you see a normal face, you see what you would expect. But as you move to your right, the nose is shifting, or not shifting, the nose looks like it's towards the left cheek more. And so because of that, you can tell that the face is stationary, that it's not following you. So as the picture on the top right shows, it looks like they're looking away from you. But for an inverted face, again, when you're looking straight at it, it looks like a normal face that's popping out towards you. But as you move to your right, the nose looks like it's closer to the right cheek, which is why it looks like it's following you as you're moving. So again, I'm going to try and show that with the camera. I can try it this way. We could try this, I think. I'm going to turn a flashlight on. Thank you. And so kind of tell, let's see. There we go. That his head is following you. No, really. I have another example as well that I can show this effect with, or a real life example is actually, if you guys have been to the Haunted Mansion Disneyland in California, there's this section where there's the haunting busts and paintings where their faces are just following you as you walk on by, and they're using this illusion of the hollow face. So now you know their secret. And so another example of this is that you can actually do at home is with the garden dragon. And with this one, we have printouts on the website that you guys can print and then cut out for yourself. But first I want to show this video to show you as how the eyes follow you. Then some of his friends join. So a bunch of eyes are following you. And again, we'll have these for you guys to cut out for yourself and look at this illusion. It's actually better on camera though. You see it more in person. It's a little harder to see. So you might have to close your eyes or close not both your eyes, close one of your eyes to see it. And this is just a huge version, which would freak me out in my living room. So yeah. Showing the back to prove it's just an illusion that is following me. Alrighty. So I want to show you guys the cutouts that we actually pre-made on the camera. So here are some of them. We have a little goat, a hippo, the dragon, and then a kangaroo. But if we could do the view from above, that'd be awesome. So here's the hippo. And again, as you can see, his head is just following you as you tilt it side to side, which is awesome. And you'll see this guy, the kangaroo. And so as I said, there on the website, you guys can find a PDF of the dragon, and it'll look something like this, and it will have instructions on whether you're going to do a mountain fold or a valley fold, and that'll tell you the correct way to fold the dragon. So maybe get your parents' help or grab some scissors. You don't need any tape. Just get some scissors, and then I would first cut out the dragon, not the instructions, because you're going to need those. And then it'll tell you how to fold these tabs, where to, how to just set up your dragon. So that'll be on the website. And that's all that I have for you guys today. Thank you.
Hi, everyone. So in just a couple minutes, we're going to have Madeline teaching us how to create your own zoetrope. So on the next slide, you're going to find the materials if you want to follow along with her, and all the printables can be found on our website at laserfunday.org. Thank you.
Okay, thank you all for coming. Today I will be telling you a little bit about persistence of vision and also making a zoetrope, which uses persistence of vision. So that video you just saw of Mickey probably looks familiar to you. You might have seen it before a Disney movie or something like that. So you might have noticed it showed one sheet at a time, and then it slowly got faster and faster until all of a sudden it was a video of Mickey on his steamboat. So that actually uses persistence of vision. So what persistence of vision is, 3 words, persistence. That means continuously, constantly, it keeps doing it. Of and vision. Vision is what our eyes do. We're all familiar with it. We see images all around us in the real world, and our eye takes those images and gives them to our brain. Vision. So persistence of vision is when our eyes hold on to those images for longer than what they are actually appearing in real life. So the human eye holds all images on their eye for about 1/10 to 1/15 of a second, which pretty much means that anything that's played back to back faster than 1/10 of a second, it looks continuous. It looks like a video. So to further explain this, I have this flip book, which is very similar to the Mickey one that was just shown. So if I just slowly flip the pages, it just looks like still images of Pocahontas. But if I flip them fast, at faster than 1/10 of a second, it looks like Pocahontas is dancing in the wind. So yeah, that is because of persistence of vision. Each page, we're holding it on our eye for longer than the period that it's being played back to back. So it looks like it's continuous. Okay, so now that we know what persistence of vision is, we are going to make something called a zoetrope, which is just a toy that uses persistence of vision and makes kind of your own little movie that's very short, but yeah. So you might have seen on the website, the materials list, we have a paper plate or a tin plate. The sturdier, the better. And then we have these printables. It's about 3 pages. And then a piece of like cardstock or construction paper, something a little more less flimsy than the printer paper. And then we have a pencil with a eraser and a push pin if you have one. It works better, but if not, no worries. And then scissors and tape. Okay, so we're gonna start with our printouts. Let's start with the first page. Here we have, this is the base of our zoetrope. Actually, first let me show you what it's gonna look like. So this is pretty much, these are all different pictures of zoetropes. It's essentially just a disc with different pictures, and when it spins, it's gonna look like a moving image. Okay, so back to our printables. We're just going to take our scissors and cut out this base. Okay, and then we have a few different choices for the next step. So this is going to be our moving image. We have horses, cats, dancers, or you can make your own. Making your own is a lot more difficult, so I don't recommend it for your first time. However, if in a few days you want to do this again and you want to do like Mickey and you want to try to make him moving or a stick person running or something like that, you can do that. But for now, it's easier to just pick one that's already made. I'm going to pick the dancers. Set this aside. Okay, so all we are going to need is these 2 strips. So go ahead and cut those out. And make sure to cut off the border. We want it to be the right size.
And if you mess up and you cut it in half, you always have 3 more pictures to pick from, so it's not that big of a deal. I'm gonna keep cutting. Okay, so I got those 2 pictures cut out. You can see if it's this way, actually this one looks interchangeable. So some of the different pictures, it matters the order, so make sure you're paying attention to that. Okay, so next we have this sheet. These 2 are exactly the same. There's an area that says overlap. Oh, later we're going to cover those up, but make sure you don't want to cut those out right now. We want to cut right along this dark, thick border. And there's these indents. Make sure you cut those wide enough. These are what we're going to be seeing through, so you want to make sure they're wide enough. Okay, so go ahead and cut that out. And I like to make sure to cut like around the black border for the indents, because for that part, honestly, the bigger the gap, the better, and then more easily you'll be able to see it. So yeah, you don't want to just cut a straight line, then you won't be able to see the optical illusion at all. So make sure you have a big gap. And then again, those overlap parts, do not cut them off. I know there's a dotted line, which makes it tempting, but do not cut them off. Okay, so once we have one cut out, we're going to do the exact same thing for this second one. It should look exactly the same. While we're doing that, I'm going to tell you a little more about the history of zoetropes and persistence of vision. Okay, so persistence of vision was first discovered by Aristotle. He did a lot of things. Pretty much one day he was outside and he looked at the sun, and once he looked away from the sun, he still had that picture of the sun on his eye, and he was like, why? So he started doing some experimentation. He pulled out a color wheel similar to this one. It probably didn't have a power drill, but you know, same concept, different colors. And then he spun it really fast. And you see how all the colors kind of combined? It was almost like a yellowish color. That's mostly because this circle is mostly yellow, but if it was different colors, they would blend differently. So yeah, he noticed that what we see is we see something for longer than the time it's actually appearing. And that's because of persistence of vision. Okay. Yeah, you probably need a few more minutes to cut this out. So I'm just gonna wait a few minutes. So yeah. Okay, probably cut it out. Okay, so now we are going to need that tape that we talked about earlier. You could also use glue or a stapler, anything adhesive. I have clear tape, so I can just, okay, so we have our 2 cutouts. Take one of the sides where it says overlap and put it on top of the other one that says overlap. And take your tape and just tape it on. And then I like to make it extra secure, so I'm going to flip it over and add another piece of tape. Okay. And then we have our two images. We're going to put them all the way to the left. So as you see, they're back to back, and this part that says overlap is uncovered. That's the way we want it. So yeah, now we're just going to tape it down. And for this part, I actually like to roll the tape behind and put it behind. But however you do it is fine, as long as you're not covering up these pictures. If you have glue, just rub that glue stick on the back and push it right on. Okay, so there's one. Let's do the second one. Okay. So now we have the most important part, in my opinion, of our zoetrope. Okay, so next pull out that piece of construction paper, and you're gonna want to cut it to be the same size as this. So I like to just put it right on top and draw a line, and then cut it out right along that line. Okay, and then we're going to want two of those, one for each part. So I'm just going to put it right on top and draw another line. And cut it out so they're the same size. Okay, so now if we look at the size comparison, it's about the same length, except we have this overlap area. That's because we overlapped part of it above. So we're going to kind of do the same thing and just overlap it so that both of the edge, like this edge, it lines up. And then if I move it over, this lines up. And yeah. Perfect. Okay. So yeah, both of them line up. I'm just going to tape it along here, and then kind of like before, flip it over, add some extra tape to make it extra secure. Okay. And now we are going to take this and put it right on top. And this is just because that printer paper is not very sturdy, so we're adding this to make it a little more sturdy. Plus, it's a pretty color, and it makes it a little more fun to look at. So again, I'm just gonna make rolls of tape and stick it behind and put it right on top. When you're taping this, make sure you don't want to just stick tape right across here, because we're actually going to cut out these gaps to match the gaps we already have in the printer paper. So we don't want to tape anywhere that's going to be cut off. So make sure you're only taping anywhere along this bottom part. And then I'm going to put one in the middle. And then I'm going to put one on the end. Okay, so now we see these two sides that say overlap. Eventually we're going to close this and they're going to overlap. So now let's go back to our paper plate and our base. We're just going to tape the base to the paper plate. This one, you can just kind of slap it on, no restrictions. Okay. So now back to our main part. Like I said, we're going to flip it around, and these parts that say overlap, we are just going to overlap them. So I don't know if you can see
But yeah, these parts are overlapping, and I'm just going to add a piece of tape here and a piece of tape right to the back. Okay. Okay, so now it's starting to look like those pictures I showed earlier. It doesn't have to be perfectly circular, it'll still work. But yeah, okay, so take our plate and we're just gonna match this right to where our base is. So just go ahead and tape it however you want. I like to just put it to the side. Maybe like 3 pieces of tape should do it. Okay, so now this is pretty secure. It's not falling off. That means we did it right. Okay, so the next step is we kind of covered up those slits that we made in our printer paper. So now we're going to take our scissors and cut those slits back out. So go ahead and just do that however you please. I like to just cut both sides and then cut the bottom. And make sure again that you're making these wide enough. Even if you have to like cut your printer paper a little, that's okay. Just make sure you're making nice wide divots because this is what you will be seeing through. And the parts where they overlap, there will be tape that you're cutting through because you had to earlier. That's okay. Just go ahead and cut it just like you will the rest of them. Okay. And this might take a minute, so take your time. Okay, and while we are doing this, I'm going to show you a quick video. Okay, so this little graphic, I'm gonna wait till you guys can see it. Okay, so this is actually 2 different images. There's an image of a bird and there's an image of a cage, and they are just played back to back really fast so that it appears that they are happening simultaneously, but when in reality, there's only one picture at a time. So this is just kind of a simple version of how this works. Our flip book showed like maybe 50 images played back to back, and this is just 2 back to back. And then the next video I have is from the slow-mo guys. So they are on YouTube. They do a lot of cool science videos if you want to check them out. But pretty much what this one is, it's a video of an old TV. And as you can see, only one line of the TV is lit up at a time. And yeah, this is very slow. Let me remind you of that. It's very slow. So in reality, it's very fast. And that's why our eyes see the entire screen lit up at once. But yeah, this is what's really happening. And if it was even slower, it would only be 1 pixel at a time. So yeah, that's how TVs work. They're not actually all illuminated at a time. They are just having 1 line at a time. Okay, so everyone should be finishing up with cutting out those divots. It should look something like this with all the different divots. So we're almost there. Now we just need that pencil with an eraser and that push pin if you have it. If you do not have a push pin, ask your parents for help,
but I like to just take scissors and make a little tiny hole in the middle, and then stick your pencil through the sharp end right up that hole. But if you do have a push pin, we're gonna take it kind of like how you would with the scissors, right in the middle where all those lines meet, stick it through, and then take your pencil eraser and stick your push pin into the eraser. Okay, so now we have a completed zoetrope, and we are just going to spin it. It's kind of hard to show on this camera, so I'm going to show you another video, but in real life, just spin it like this and look through the sides, look through these divots. If you're having trouble seeing it, maybe make the slits a little larger. But yeah, you should see a continuous motion of the people dancing or whatever image you chose. So here's what it should look like. Here's a video from me earlier today. So I did the horses, and as you can see, it looks like the horses are galloping. I'm not swirling it continuously, but yeah. So I hope you're all able to do this at home. And finally, I'm going to show you another video of zoetropes. This one is a 3D one. So this person actually was an artist, and they made these frogs and lily pads and everything and put them all together. And then how our zoetrope works is we have those slits so that you're either seeing it or you're not, back and forth. But this is actually going to use a strobe light, so it has the lights on and off. And yeah, in a minute, he's going to speed up that circle. And then once it gets to the right speed, it actually looks like the frogs are moving. So yeah, see, they're actually just different positions of the frogs, but played back to back, it looks like the frogs are moving. So that is all I have for you today. Thank you all for watching my demo, and look forward to the next one. Hi, everyone. Next up, we have Alyssa teaching us about total internal reflection. We're going to put up a slide that has a few materials you'll need if you want to go along with us. Otherwise, just enjoy the demo. Thanks. Okay. All right. Good morning, everyone. My name is Alyssa. Maybe good afternoon. My name is Alyssa, and I'm going to be talking a little bit about total internal reflection today. So before I get going, some things you're going to need, it was on the previous screen, but if you have a fish tank or even like just a clear glass container and some water you can fill it up in, that would be great. Also, if you have an empty milk jug, and you can just go ahead and fill that up. We're going to poke a hole in it later. So if you can have an adult help you get a pair of scissors as well. So those are our supplies along with our laser if you have it. So maybe if you guys don't have that yet, you guys can kind of get that together as we go through. Okay, so a little bit about total internal reflection. We're going to break that down, what that means.
So we have total internal reflection, or TIR. So we have T for total, and then we have I for internal, and then R for reflection. Okay, so what do these mean? What do these words mean? Let's break them down individually. So when I say total, what do you guys think of? Think about it at home. I think about like everything, right? Total involves everything, the sum, all that. So we're going to say everything. Okay, so everything, and then what about internal? So internal is the opposite of external. So external is outside, internal is inside, right? So inside. And then we have reflection. Reflection isn't as straightforward, right? It's like total. But when I think of reflection, I think of a mirror. So I wake up in the morning, throw my hair up in a ponytail, and whatever I am looking at, that image is coming back to me. So we're going to say reflection comes back. Okay, so total internal reflection, or everything inside comes back. That's kind of the idea that we're going to go with. So I'm going to go ahead and draw something, and we're also going to use our imaginations a little bit. So I'm going to go ahead and just show this lovely picture of some water. As Tucsonians, all of us in Tucson don't necessarily have an ocean, but maybe you guys are watching from somewhere else. If not, you can imagine a sea, an ocean. It's almost summertime. It's beautiful weather. And we're going to picture that we're out playing with our friends, and we go underwater, and we start looking up at the water, right? So kind of what we're seeing in this picture here. So we're laying on that like rocky bottom and looking up, and we can see the water surface. We can see the reflections occurring. That's the scenario that we're going to be talking about here. So I'm going to draw this water, right? So we got blue water going on here, all the way across. And we're going to talk about 3 different cases. So the first thing we're going to talk about is if you were to go underwater and you had a nice waterproof laser and you were to point it pretty close to straight up. It might be at a little bit of an angle. So we have just a relative line straight up, and we're going to have the laser going. Laser is going to go just at a pretty small angle here, right? So then it is going to just come straight out of the water. So if there's, someone above you, then they might be able to see that laser that's coming straight out. So that's the first scenario. And then the second thing that could possibly happen is if we make that angle just a little bit larger, so it's not going quite straight up, but it's a little bit larger. So we're going to go here. At a very specific angle, that light is actually going to kind of stay along the path of the water. So again, if you have your laser in there, you might actually be able to see, like, this is a green laser, right? So you might be able to see green specks along the water. So this is the second scenario. So this is 1, this is 2. And now we have total internal reflection for 3. So for our third one, we are going to imagine that we make a much larger angle, larger than this angle on the second one. So once again, it might be like pointing it, like this instead of pretty close to here. So we have this angle coming in. Oops. And what is going to happen is total internal reflection. So everything inside comes back. So meaning everything, as in the light, inside the water is going to come back in the water, stay in the water. So that light is actually going to bounce back this way. It's all going to stay in the water. It's not going to necessarily go into the air like you would imagine. Okay, great. So hopefully, we enjoy some nice pictures, but let's actually look at what is happening. Let's do an example. So we're going to go and take that fish tank or that cooking pan or whatever you have at home and fill it up with a little bit of water. Oh, and additionally, if you don't have it, it's fine. But if you have any type of like milk or creamer or anything along those lines, we're going to use a few droplets of that just to help us kind of see what's going on. And it just looks a little bit cooler. So I'm going to go ahead and turn off the lights while you guys kind of get the supplies. So we're going to have a fish tank or a pan fill it with a little bit of water, laser, and milk. Okay, so I'm gonna go ahead and turn off the lights. Okay. Okay, awesome. Okay, so here we are. So we're gonna take that milk and we're gonna just put a few droplets in there, okay? I'm gonna very carefully, might be a little much. Okay, so I'm gonna go ahead and take my laser and I'm just gonna start pointing and we're gonna see what happens. So first I'm gonna point my laser straight through, right? And hopefully you guys can see it's lighting up, especially if I go through the milky cloudy part. But we're trying to look at total internal reflection. So I'm gonna go ahead and start tilting this laser upwards. So as you hopefully can see, the light is actually hitting the surface, I'm sorry, take my hands, kind of over in this area where this bright spot is, but it is actually reflecting back down. And you can see that how it's coming out where my hand is. So this path is more like triangular. So it's hitting the surface and then it's bouncing out over here. Yeah, hopefully you can see that over here on my hand. Okay, sweet. Hopefully you guys are able to see this at home. This is super cool. Looks like a little jellyfish are in here. Okay, perfect. So let's talk a little bit about why this can happen as well. Let's talk about light a little bit, right? Laser fun day, we have to talk about light. So light travels super duper fast, like faster than I can comprehend. So we're just gonna kind of like think about how fast you think light might run. I run at like, I don't know, a couple 100 miles per hour, but light goes even faster than I do. So we're gonna say, figure out how fast light goes in meters per second. So a meter is like, right, yay big. So we're gonna pretend we're gonna see how many meters light can cover in 1 second, right? So I'm just gonna start throwing some numbers up here. So light is gonna travel at 3, and we're just gonna keep adding zeros until we travel at the speed of light. Okay, so we're over here. So we're at 300,000 right now, and we're just gonna keep going, add some more zeros. So light actually travels at approximately 300 million meters per second. And I can't comprehend what that number is, so we did a little bit of more math. And let's see. Okay, I think on the screen. So up here we can see that the speed of light in air is about that 300 million meters per second. And what that means is that light could literally travel around the Earth 7.5 times in 1 second. So that's just kind of like a crazy number to comprehend, right? But what's cool about light is it acts a little bit different in different properties. So for example, we just looked at water, right? Like we're looking in our pool, we're looking in our fish tank, and light actually travels at a different speed in different materials. So for water, it's a little bit slower. So it's about 225 million meters per second. So I don't know, I think someone could probably take it in water, but that means that it can travel around the world about 5.6 times in 1 second. So it's a little bit slower, and because of this difference in speed, that is what's helping us have total internal reflection. So that's great. Total internal reflection, you can see that if you bring, waterproof laser underwater in the summer, but what other good is it for? It actually has multiple applications, and let me go ahead and take this down. And one of the most useful applications of total internal reflection is actually in communication systems. So basically, there are these fibers, is what they're called, look kind of similar to this. They're just, they're not straight. They have, the glass inside of them. And they actually are like throughout the world. There's actually some that just lay across the bottom of the ocean, which just kind of blows my mind. And it is able to actually transmit data by using light. And so this is a very effective way to do this because light travels so fast. So you're able to get data, in far places very quickly. And so this rod that I have here is going to kind of show this. So once again, we're going to shine the rod straight through and we can see it coming out, hopefully. Okay, so if I were to tilt this, as you might remember from the water examples, is very similar. If I tilt it, then that light is going to bend and reflect back down. But this rod is super cool because the more I bend it, you can see that there's more and more that there are more and more like bends of light, and it keeps bouncing. And so this is actually like what is happening in those fibers that go across the world. So here, like I showed you guys earlier, but let me put a light in here so you can see. Okay, so as you guys can see, I have this light and I'm shining it right here into this like fiber system. And we can see that even when if I keep the laser on it, if I move this, then that light is continuing to go through. And this is because there is that total internal reflection just occurring throughout this. So this is kind of how fiber optical communication systems work. That's super cool, right? But let's talk about one other cool example, something that all of us love, and that is pretty colors. So when we're looking at this example, right, this is Disneyland, Disney World. At nighttime, they have these gorgeous shows, but what's actually happening? How is this water different colored lights, right? So this is actually total internal reflection. So there are lights that are at the bottom of these waterfalls, water springs, don't know the word right now, and it's actually totally internally reflecting through that water. So we're going to also go ahead and do that example. It might not be quite as good as Disneyland's waterfalls, but we're going to try to make it. So we're going to go ahead and get out our bucket of water, gallon of water, and we want it to pour into something. So you can do this over the sink, you can do it over the bucket, you can do it outside. I don't recommend doing it outside actually if you want it to be in the dark. So we are going to take this and grab my scissors really quick. Okay, so I recommend having an adult help you, but some things before we do this is you want to make sure to poke a hole on a side that does not have like the sticker on it. So we want to be shining a light through a side with a sticker, and we want it to come out with the side without a sticker. So I'm going to go ahead and just like put it on its side. Okay, hopefully you'll make less of a mess than I am. And you're just going to go ahead and poke a hole just a little towards the bottom. It doesn't need to be super high. You want to make sure that that water is going to cover it. So with an adult help, you're going to poke a hole, hopefully smaller than that one I just made. Okay, great. So time to make your own laser waterfall. So I am going to have some help to hold this just so I don't spill everything. Okay, so if you hold the bucket, and then I'm gonna switch to the version. Okay, so we're gonna hold the bucket and we're gonna turn those lights off. Okay, so your water's probably coming out a little bit, and that's okay. We're gonna take the laser from the back and shine it kind of through the hole. You may need to kind of like press the bucket to get some spouting to go on. Let's see. Yeah, you can see that. So this is total internal reflection of our at-home Disneyland waterfall. And so what is happening is that light is shining through and it is bouncing off the waterfall as it's coming out. And so this is obviously a very small scale example of what's happening, but this is kind of a pretty part of optics, right? Oh, sorry, thank you. So yes, you can see optics pretty much anywhere. I know here at the University of Arizona, we have that waterfall out by Old Main, and at nighttime it has the different colors. Like I said, you have Disneyland. And so basically optics is anywhere, right? It's anywhere from across the bottom of the ocean, like with transmitting data through light, and it's in the waterfalls. It's when you're underwater and you're playing. So I hope that you guys got to learn something today. I hope you get to look for light anywhere you go now. Maybe next time you think of a waterfall, you can tell your friend about total internal reflection. And that's all I have for you guys today. So thank you for listening.
Hi, everyone. Our next demo is going to be in about 15 minutes, and it's going to be a super cool video of a cow eye dissection. So stay tuned, go grab a snack while you wait, and enjoy. Thank you.
Hi everyone, my name's Jenna. I'm a first-year PhD student here at the Wyant College of Optical Sciences, and I'm here today to show you the parts of a cow eye. So I'll do a little dissection, and we can talk about how you can see everything around you, because our eyes are very similar to cow eyes. So first I want to talk a little bit about how the eye actually moves around to look at different things. There's a lot of muscles, as you can see in this diagram, around the eye that pull it in different directions. And there's 6 of them. And there's also muscles that open your eyelids, because that's important. And that's that. I have already cut off all of the muscle from the outside of the eye, though, because that part is a little bit boring. So next, I want to talk a little bit about how light gets from the front of your eye to the back. So first, the light hits the cornea, which is the outer surface of the eye, and it bends the light through the anterior chamber, which is full of a fluid that's kind of like water. And then it goes through the iris and the pupil. So the iris is the colored part of your eye, and the pupil is the hole in the middle of it. And the pupil allows the light to pass through to the back of the eye. And as you know, when it's darker, you might notice your pupil gets bigger, and that's to let in more light because there's less light available. So the iris is actually a muscle that gets bigger and smaller. And then the light goes through the crystalline lens. So the muscles on the top and the bottom of the lens in the diagram, the ciliary bodies, pull the lens so that it changes shape, and it can focus objects from different distances to the retina, which is your sensor. And it goes through the vitreous cavity before it gets to the retina. That's just full of another water-like fluid. And then it gets to your retina. So the retina contains photoreceptors which sense the light, which we'll talk a little bit more about later. But the main thing is that the light that is focused by the cornea and the lens ends up at the retina, and that's how you sense the light and things going on around you. And then that information is sent through the optic nerve to the brain. So your eye as an optical system is not actually that good, but the brain takes the information from both eyes and puts it together to give you things like depth perception, and it fills in some blanks of things you can't see. So it's really cool. Okay. So now I'm going to dissect the eye and show you some of the components that we were just talking about. So first, this is the eye. You can see the cornea is here. It's cloudy right now because it's detached from the cow, but typically the cornea is clear. And then this is just the sclera and the surrounding tissue. And then on the other side, this is the optic nerve. So this is the nerve that we talked about that transfers the information from the retina to the brain where it gets processed. So what I'm going to do is, here's the cornea, here's the optic nerve. I'm just going to cut down the middle with a scalpel, and we're going to see some of that vitreous humor come out. I'm just going to go all the way around. And you can look and see some of the muscle is still here, the muscles that we talk about that move the eye around while you're trying to look at different things around you. Almost all the way around. Okay. Oops. All right. So here is the front of the eye, and here's the back of the eye. First, let's start with the front of the eye. So I'm just going to empty out this fluid here. So this contains nourishing chemicals for your eye, and it also helps to focus the light. It has an index of refraction similar to water. You can see it looks kind of watery. So just clearing that out, and then we should be able to grab the lens. Oh, here, I'll take this out. Take this layer out. We'll talk about this layer later. All right, so here and here, so you can still see the cornea is here. That's the only thing that's really left inside of the eye. So the cornea, again, is just the outer surface of the eye. It has a dual purpose of protecting your eye from bacteria and stuff like that, and starting to bend the light towards your retina. Okay. So then this thing that I took out must be the lens. So the ciliary bodies are long gone, but remember this is connected to the eye through the ciliary bodies or ciliary muscles that will stretch the lens into different shapes. At this point, the lens is pretty rigid, but in a living eye, it's pretty squishy, so that it can deform into different shapes to, again, focus the light to different directions. Kind of like, so if the light was coming through this way, you can imagine that if this was less of an oval and more curved like a sphere, the light would end up at a different location. And we can talk about that a little bit more later too. I've got some slides on that. So that's the lens. And then this, you can kind of see the iris here. And this, in a living eye, changes shape. It gets smaller and bigger to change the size of your pupil, which is just the hole. So this part, this center part, that's just a hole, looks black in your eye, but really it's just a hole that lets the light through. And then if you're in dark environments, this can get bigger to let more light in and reduce your image quality, which is why you can't see as well at night. So there's the front of the eye. The only thing we didn't talk about is this stuff around here. This is just the layer of blood vessels. Blood is a substance that contains a lot of nutrients and can provide extra nourishment for your eye. So that's the front of the eye. We're done with that. And now we're going to look a little bit at the back of the eye. So this surface, this first one, is called the tapetum lucidum. And what it does is it reflects light. So if you notice, some animals, their eyes glow at night, like cows and cats. Or if you have a cat and you use flash photography, you notice that in that picture their eyes just light up. That's because this layer is highly reflective. This one under here, behind the retina. It's a really pretty color. And it's nice and shiny. Okay, so this piece that I'm peeling away is the retina. So this is full of tiny microscopic rods and cones, which are the photoreceptors that gather the light. Rods collect black and white light, and cones collect colored light. So people who are colorblind have problems with their cones. And when you see at night, you tend to use your rods, which is why at night things look black and white. And yeah, so then this here. Remember, we've got the optic nerve on the other side. But this isn't exactly lined up with the optic nerve, so what could this be? This piece right here. It looks like everything is converging to a point. Well, near the center of the retina, there is the macula and the fovea. And the fovea is where you have the highest density of rods and cones. So in the outer edges of your retina, where you have more of your peripheral vision, you have just kind of like sparse rods and cones here and there. But then when you get to the center here, there's a ton of them, which is why when you look straight at something, you can see it pretty clearly. And then while you're still staring at that and trying to figure out how good your visual acuity is in your peripheral vision, like on the edges, it's not as good because all of the rods and cones are centered right here. So that is why your peripheral vision is not as good. You might be wondering why we don't just have more rods and cones at the edges of our vision. The limiting factor is actually not the rods and cones being less dense. The limiting factor is that, like I said, our eyes are not the best optical system. They don't focus the light very efficiently. So at the edges of an image, we don't really have that good of a resolution. We can't see things as well. Okay. So there goes the retina. And this part right here looks like the part that's connecting to the optic nerve. So this part, all of the information gets sent straight through here and out the back to the brain. And an interesting part of this is that you can't actually have any rods and cones where you're sending the information to the retina. So like, imagine you've got a map full of different receptors, and then at this spot, you have to collect them all and send them to your brain. So at this spot, or at this spot in the eye, you can't actually see anything, and it's about 15 degrees from your central vision. So you can actually test this if you want to by looking straight down and putting like a coin, like a penny over here, like about 15 degrees. And then you try and look straight down and you notice that you can't actually see the coin. That's because that's sending the information to the part of your retina that doesn't have any rods and cones. It's the blind spot. So that's pretty cool. That's some cool stuff. And below this is just black. And the reason why this is black and not the same color as other tissue, like this kind of grayish, maybe pink, is because black doesn't reflect any light. Black absorbs all of the light. So all of the light is contained in this cavity of your eye, and it's not getting into the tissue and messing with it. So that's why it's nice to have a black outer layer. Okay, so I think we're done with the dissection, and maybe we can discuss a couple other things that we saw. Okay. So, like I was talking about earlier, that really pretty, like, blue layer is why some animals' eyes glow at night in the dark. They're reflecting all of the light, so that part's cool. And this is, since we couldn't see inside of a living eye, this is a picture of a retina. And this is actually, if you ever go to the eye doctor and they dilate your pupil and they look inside your eye, this is what they see. And that dark spot is where you have a lot of rods and cones in the macula. Okay? And then this over here, notice that there's a bunch of blood vessels coming in here. That is the blind spot. So that's where your blood vessels and your nerves are collecting and eventually being sent down to the brain. So, like I was talking about earlier, rods are responsible for low light and black and white, which is called scotopic vision. And rods have low spatial acuity, which means that you can't see as well with your rods, with your black and white or your night vision. And cones are primarily responsible for color vision and more active in high light level setting, which is called photopic vision. If you have the lights on in the room right now, you're using photopic vision, and you can see lots of colors. And if you turn the lights off and it's dark outside, you will probably be using your scotopic vision, and things will look more black and white and a little more fuzzy. There are 3 kinds of cones as well, the S, M, and L cones, and those are just responsible for seeing different colors or different wavelengths. So maybe if everything around you is blue, you're really just using your S cones, but you can have M cones and L cones for red and for green. The fovea is the center of the macula, where you have all of your rods and cones. The optic disc, we talked about that. That's the blind spot where the optic nerve and all of your blood vessels enter the eye. One interesting thing that your eye does is it inverts the image. So basically, when you look at something and that information is sent to your eye and your eye focuses it on your retina, the image on your retina is upside down. So if you looked at a tree on your retina, you would see an upside down tree. And then when that image is sent to your brain knows it's inverted, so your brain flips it back around for you so nothing looks upside down when you're looking around everywhere. If you can't see far away, you might be nearsighted, which is called myopia, which basically just means that, remember we were talking about how your lens can accommodate seeing things maybe close up, maybe far away, different distances. Well, people with myopia or people with hyperopia have a different eye shape to which the lens can't focus exactly on the retina. So in myopia, you can see that the light is focusing a little bit before the retina, and the lens can't change its shape anymore. So that's why, because at that little tiny point where everything is converging, that's where you would be able to see everything really well, but your lens just can't change shape enough for you to be able to see that. So, and then with farsightedness, it's the opposite problem. So your eye is at a shape where the light is focusing behind the retina. So you can correct these with lenses. So remember myopia, we were focusing before the retina. Now we're focusing exactly at the retina because we add a negative lens. This is So if you can't see far away and you correct it with glasses or contacts, it's probably a negative lens. And then if you are farsighted, so you have trouble reading really close up, you might have reading glasses which are corrected with a positive lens. And you might see, next time you go to the drugstore or the grocery store, if you see reading glasses, you'll see different prescriptions and they say like +1 diopter, +2 diopters. That's because they're a positive lens. And if you have myopia, you can't see far away, you might look at your contact lenses and see a negative number. I really can't see, so mine are -6. I'm legally blind, I'm pretty sure. So thank God for contacts. But you might see a negative number on that or on your glasses prescription, and that's what that means. It's a negative power lens, so it brings the focus to your retina. Okay. And there are some other interesting things to research about the human eye. If this demo has inspired you to do more research, these are some really interesting things to look at, like optical illusions. A lot of optical illusions, they trick your brain into thinking that things are there or things aren't there. Because remember I was talking about how like your brain can like fill in the gaps. Like if you see a bunch of stripes and then you can't see behind the stripes, you'll assume that the spot that you can't see is full of stripes. That's one of the classic optical illusions. Astigmatism is when your eye can't focus. It doesn't focus the same in one direction versus the other. Your cornea is a weird shape. I have astigmatism. Cataracts is a problem with your cornea. Glaucoma, similar problems with your cornea. Color blindness. Remember we talked about your cones are in charge of color vision, so people with color blindness have problems with some of their cones. And LASIK. LASIK is laser eye surgery where they cut a flap into your cornea and then they change the shape, basically, of your cornea so that if you're myopic or hyperopic, usually they do it with myopic people, you can see without wearing glasses because it changes. Remember we were talking about how changing your lens shape will change where it's focusing. Well, they change your cornea shape and it has the same effects so that you can see without glasses. So that's pretty cool. Okay, well, thank you for watching this demo. I hope you had a good time, and that's all.
Hi, everyone. Next up, we have Christian teaching us how to measure the speed of light with a microwave. We're going to throw up some slides again with a few materials you can collect if you want to come along with us. Otherwise, enjoy. Thank you.
Hey everyone, my name is Christian. I'm a PhD student here at the College of Optical Sciences. And today we're going to measure the speed of light with a microwave, a candy bar or chocolate bar, whatever is your favorite, some plates, and a tape measure. So this is a pretty cool demonstration that will get a value close to the speed of light that a lot of astronomers and scientists that were around many centuries ago would be very jealous of. So let's get started. So I first want to talk about just how cool the speed of light is and how basically special of a measurement this is. The speed of light has fascinated a lot of people for many, many years. For a long time, people thought light might travel even infinitely fast because it was just seemed to be so fast. And it wasn't until about the 1600s, so really not that long ago in the grand scheme of things, that people actually were able to make the first measurement of the speed of light. And it does seem to be incredibly quick. Scientists now have measured it to move at 300 million meters per second, which is enough to travel around the world 7 times in 1 second. It can travel from here to the moon in under 2 seconds. And because it's so fast, it's one of the reasons why light is so useful to us. The reason that you can hear and see me now is because a lot of the information being sent over the internet, including this video stream, travels on basically beams of light through cables. If you watch the total internal reflection demonstration, you got a sense of how beams of light can propagate through these little glass fibers and make up the entire internet. If you use a cell phone to make a call to somebody or a video call to someone, that's also transmitting light and radio waves, as we'll talk about in a second. And they travel fast enough to make this seem instantaneous, or the talking between you and the other person seem instantaneous. So light is really fast. It's even faster than a lot of the other things that we might consider being fast, like sound, for example. If you're in Arizona in the summer and you see a thunderstorm, the sound of a thunderbolt will get to you a couple seconds after you see the flash from the lightning. And so that tells us that the light is traveling much faster than sound. And everybody knows, like, sound travels pretty fast. If you're talking with somebody across the room, it seems like they're just talking instantaneously with you. Okay, so now that we have a little bit of understanding just how fast light is and how cool it is to make a measurement like this, I want to talk a little bit about waves. And the reason that waves are interesting is because light is actually a wave. And you may know this, and you may also know that waves are all around you. There's so many things in nature that we can accurately describe as waves. If you've gone surfing, you've ridden on waves that form in the ocean. Sound is also a wave. Earthquakes, you can actually see, like, in really big earthquakes, you can see the earth moving in these wave forms. If you've played guitar, like, the strings on the guitar will form waves as well. So waves are just everywhere. And including light is also a wave. And there's a couple things that I want to talk about with waves. And so let me just draw one on the board to start off. So here we have kind of a sample illustration of a wave. And the two things that I want to talk about with waves are, first, 2 different properties are the wavelength, which is the difference, the distance between these 2 peaks here. So that's the wavelength. And then the next property I want to talk about is something called the frequency. And the frequency is basically, so as this wave, this is a snapshot of the wave in time. And as the clock ticks forward a little bit, this wave will start to move. And the type of wave that's in our microwave, as we'll talk about in a few minutes, what it'll look like after a little bit of time is maybe something like this. And so these peaks will move down, and then eventually it'll get to a point where it's flat. And then it'll have peaks kind of in the other direction. And eventually they'll reach the same height, but just in the exact opposite direction. And so this, if you follow a point on this wave, it'll kind of move from here, down to here, down to flat, down to here, and then back up again. And it'll keep doing that over and over and over. And the number of times that it goes from this point up here, down fully to here, and then back up again, that's called the frequency of the wave. So if you have a wave that goes and all the way down and back up again 10 times in 1 second, we would say that wave has a frequency of 10 hertz. And the unit hertz is basically just means the number of cycles or the number of times this goes up and down per second. So now we know about the wavelength of a wave and the frequency of a wave. And the reason why we want to know these is there's a really cool relationship between the wavelength and the frequency and also the speed of the wave. So if you take the speed of the wave, and I promise this is the only math you need to know for this experiment today. The speed is equal to the wavelength times the frequency. So this is true for all different types of waves. And so this will help us to measure the speed of light because light is a wave. And we're familiar with the light that we can see very well. For example, you can see blue light or red light or green light. And those forms of light have wavelengths that are measured in about hundreds of nanometers. So 1 nanometer is a 1 preceded by 8 zeros. So it's a really, really small unit of measurement. It's much smaller than, for example, the width of your hair, thousands of times smaller. So red light, for example, is going to have like a wavelength of 700 nanometers. So that's very tiny. And what differentiates red light from, say, blue light is the wavelength here. So it's the distance between the peaks. So let me just kind of illustrate that. So for example, if we had blue light, the distance between these peaks is going to be something like that. And if we have red light, the distance is going to be longer between them. And that's what like differentiates them. That's what makes them different. And we have cells in our eyes that can tell the difference between waves that have a wavelength like this, like the red light, and the blue light. But there's also a lot of other different forms of light. And you may be familiar with some of them. For example, radio waves are also a form of light. And they have a wavelength that is around a few meters. Infrared light, if you've ever seen like night vision goggles or night vision cameras, infrared light is emitted by hot objects. And so you can see them even when there's no visible light. And so they have a different wavelength than visible light. X-rays, also a form of light. And the X-rays actually have really, really tiny spacings between these peaks here. And it's really useful, in fact, for imaging the bones in your body. And so there's so many different forms of light, but the only thing that makes them different is that is this wavelength, the spacing between them. And so microwaves are also a form of light. And it turns out microwaves, like that are emitted by your microwave, are really useful for heating up things, which is why we have microwave ovens. So now we're going to get into the meat of the experiment here. And so if you have a microwave in front of you, you're going to need to try to, or the first thing we're going to do is get the frequency of the microwave. And the frequency of the microwave is listed on the back. And so if you have your microwave in front of you and it's easy to get to the back, go ahead and get in a position where you can read the label. I'll flip it like this so that we can kind of see together what I'm looking at. And if you can't get to the back of the microwave, don't worry, most of them use about the same frequency of microwaves. And so you can use the value that I'm using here. So you can see here next to the output power, says this one's a 900 watt microwave. And you'll see a number followed by MHZ. And that MHZ stands for megahertz. And 1 megahertz is 1 million hertz. So that's 1 million cycles per second. So the light emitted by this microwave has a frequency of 2,450 million cycles per second. That's really fast. And so that's a pretty standard frequency. So if it's hard for you to get to the back of your microwave, don't worry, you can use that value and you'll get pretty close to the answer that I'm going to get here in a second. So now that we have the frequency of our microwave, now we need to determine the wavelength. So let me just plug in the microwave because you're going to need to use it in a second. And so now's the fun part, determining the wavelength. So you'll need to get your chocolate bar. And I've already gone ahead and removed this kind of central plate and the thing that it spins on. This helps you, when you're heating up your food, spins around and helps to heat it evenly. And we don't want to do that. And you'll see why in a second. So take that out and set it aside. And then unwrap your chocolate bar. And you're going to want to set it kind of in the center of the microwave. So we've got our chocolate bar. And I've got a paper plate here, kind of makes cleaning up a little bit easier. So set it on the paper plate. And you can put it in the center. And this setup, it's upside down on the paper plate. And this setup makes it just kind of simple to ensure that the chocolate bar doesn't rotate around and that it just heats up in 2 different spots. Or just heats up in the same spots as opposed to spinning around. And the orientation of the chocolate bar is also important. There are these holes on the side of the microwave, and there's some on the other side as well. And those holes are where the microwaves are actually emitted from. And so if we're thinking about our picture of a microwave, or a picture of a wave, there's waves emitted here, and they should have the peaks and valleys that kind of set up across the microwave in this direction. So they're emitted on one side and sort of absorbed on the other. And some of them are absorbed by your food, which will heat them up. So now I'm going to close the door and set it for about 45 seconds. You might have to play around with this depending on how much power your microwave has. And hit start. And now I'm going to talk a little bit about what we expect to happen. So we have a bit of you probably have a bit of an understanding that light carries energy, and waves in general carry energy as well. If you've ever been outside in the summer in Arizona and stood in the sun, you know light has a lot of energy. It heats up pretty fast out there. Also, if you've ridden on a wave on a surfboard, you know that there's certain parts of the wave that have more energy than others. So if we go back to our illustration of kind of what a wave looks like, we've got these areas right here. Remember, this is our wavelength. We've got these areas that move a lot, and then other areas like right here or at the edges that don't move a lot on the wave as it oscillates. And so if you have been on a surfboard or seen people surfing, you know that you go pretty much the fastest when you get close to these peaks. If you're out in the ocean and it's flat, you don't go very fast and you don't get a lot of energy. But when you try to catch a wave, you get on these peaks. And this is where the energy of the wave is. And so it's these spots in the microwave that carry the most energy, and those spots that heat up the food the most. So if we go back to our chocolate bar, so we can see that we can zoom in a little bit. You can see that it's started to melt, and there's kind of a central area of melting here. Kind of see it glisten. So it's melted a little bit in the center because I probably had it in for a little bit too long. But there's an area of kind of central area of melting here and central area of melting here. And those spots correspond to the points on the wave that carry the most energy. And those points are spaced one wavelength apart. And so if we measure the distance between those two spots, as you can see here, like mine is a little smeared out. So you want to try to get, this one's pretty clear, but it looks like this one kind of hit the edge of the paper plate. So do your best and kind of measure towards the center. I'm going to take my ruler or tape measure and try to get a good estimate of the center of the two. So I've measured it, and from the centers, it looks about 11 centimeters apart. And so now we have the two ingredients in this equation to find the speed of the wave. We've got the wavelength, which is 11 centimeters, and the frequency, which was listed on the back of the microwave, and you can use a value of around 2,450 megahertz. So now I'm just going to multiply the two together on my computer. So take, you want to find a value, well, usually scientists work in meters per second. So take 0.11, so 0.11 meters, which is equal to 11 centimeters, times 2,450 followed by 6 zeros, because it's 2,450 megahertz. And we get a value for the speed of light. That is, the value that we found is 265 million meters per second. And this actually compares pretty well with the value that scientists use a lot for the speed of light the speed of light, which is 300 million meters per second. And so with just a microwave, candy bar, and ruler, we're able to get a value for the speed of light that a lot of astronomers and physicists not that long ago would have been pretty jealous of. So thanks for following along, everyone, and I hope you enjoy the rest of the demos.
Hi, everyone. In about 5 minutes, we're going to have our next demo, which is creating your own 3D glasses, which is going to be super fun. So make sure you go and get your materials all set up for our demo. Again, it's going to start in about 5 minutes. Thank you.
Hey everyone, and welcome to Laser Fun Day. Hope you've been having fun doing all the other demos, and I hope you're really pumped for this next one. Right now, I'm going to teach you how to make your very own pair of 3D glasses. But before we get started, let's find out exactly why we see 3D images from the movies. So I want to talk about something called stereoscopic vision. Basically, what that means is that because our eyes are offset by about an inch or so, the brain receives two images. These two 2D images then get processed by the brain, and the brain gives it depth perception. So basically, in those old school 3D movies where you would see these glasses with one lens cyan and the other one red, it's exactly kind of copying that same process that your brain does. So what happens is that the projector of that movie puts out an image in two different colors, one cyan and one red. Then it uses a lens system such as the glasses to basically called filter out the color. But what that really means is just you have blue light come in here and hit this cyan lens, and then this cyan lens blocks this blue color or cyan color. Basically, this either bounces it off or it stays here on that lens and hangs out with it, but it doesn't allow it to go past that lens. And so the only colors that you really see is that red color. And the same goes for this red lens. It blocks that red color, and what you'll end up seeing is that cyan color. Okay, so now that we know a little bit about how that works, we can talk, or we can go over how to make your very own pair of 3D glasses. So I hope you've gathered your materials. You'll need some cellophane, which is just basically a clear plastic material used in packaging. You'll need 2 pieces of paper, some tape, and then 2 permanent markers, 1 red, 1 blue, and your pair of scissors. All right. So to start off, we'll start off with one of the papers, and we're gonna fold it lengthwise. So I know some people are familiar with how they say hot dog style. So you're basically gonna fold it that way. Just be sure to leave that edge clear right here. Make sure to leave that clear and not fold over it. So you'll have your paper like this, and then we're just gonna do a crease going down the middle. This will be our center. So the next is we have to, and feel free to cut this however you want. You can cut out the edges to make it whatever length you want. You know, I prefer my glasses big, so I leave it like this. But you can cut it however you want. So the next step we're gonna do is we're gonna cut out a piece for our nose. So I just go down the center, cut a triangle. And there you go. That's where our nose will go. Okay, so then the next step is to cut holes for the eyes. So what I like to do is I just put it up against my face and I measure it. So my eyes will probably go around here where my thumb is. And then I just fold it. And you're gonna cut 2 lines right there. Fold it. And cut it. So that we have 1 hole right here. And then we'll do the same with the other. And we're gonna fold it so that we're even. Have that folded. Again, cut two lines right here. Fold this over and cut it. So now your glasses are starting to take form, but now we got to add the lenses. So the lenses, this is where that cellophane comes in. So you kind of want to see how much you're going to need. So you open up the glasses, kind of figure out, and you're just going to cut a square big enough to cover that hole. And then just double checking. That's good. Then we'll do the same for the other hole. So cut it. Okay, So we have our lenses. Now we have to color them. So when you're coloring, just make sure to cover the entire plastic. And let me get. So yeah, you want to be able to spread that the color red over that. And then the same goes for that color blue. Okay, so now we have 2 lenses. And then one important thing to remember is that the red lens is going to go on the left side, and then the blue one will go on the right. So yeah, make sure not to mix that up, and then just flip them over so that you don't get any ink on your face, and then just tape it inside there. Right, nice. So now we have that done. We're gonna close our glasses by taping that edge that we left earlier. So we have our glasses here. And then the last step is we're gonna have to create kind of like a strap to go on the glasses to fit around our head. So you'll take that other piece of paper. You're gonna do one fold this way. And then cut that along that edge. Okay, so we have our 2 kind of straps here. We're gonna tape each one at each side of the glasses. Another piece of tape. Okay, and now the last part we do is we'll fit this over our head and measure where the two straps meet. So that's that edge right there for me. Try it on. And there you go. You have your very own pair of 3D glasses. And it's kind of big, kind of look like a superhero with 3D vision. But make sure to try it out. You can, on our website, we have a link to some 3D drawings. You can check those out, or you could do just a Google search, check out 3D drawings. You can, and just see, and then you can show off to your friends, see what you created. But I hope you enjoyed it, and I hope you enjoy the other demos coming. Thank you and have a good one.
All right, everybody, we're going to start the next demo just a little bit early. We have Miss Miriam. She's going to show us how to make your very own pinhole camera. We're going to put up a slide again with some materials that you may need, so look out for that, and we'll get started very soon. Thank you.
Cool. All right, so hi everyone. My name is Miriam Baker, and today I'm going to be showing you how to make a pinhole camera using a Pringles can. So first, let's talk about what a pinhole camera is. So a pinhole camera is a camera that forms an image using a pinhole, or just a hole in a material, instead of using a lens. So light from an object passes through this hole, and an image is formed on the screen. So how does this work? Well, everything has light coming off of it. If you've ever seen Inside Out, you'll notice that Joy kind of has this aura, or all these little pieces of light coming off of her. And in reality, everything has light coming off of it. So a pinhole camera takes some of that light and samples it through that hole and directs it onto a screen. And that's how we're able to form an image without a lens. A pinhole camera is also called a camera obscura. And a really interesting piece of information is that historians think that artists used pinhole cameras a long time ago because their paintings had the right proportions. So they didn't think that it was very likely that somebody was just looking at a landscape and was able to get the proportions perfectly. And so this pinhole camera was kind of like an early projector. So before we build our own pinhole camera, I just wanted to show you what one kind of looks like. So here's a Pringles pinhole camera that I made, and I was looking at my backyard, which is this picture on the left. And so on the right is a video of me looking through this pinhole camera. So you can kind of see like that palm tree there. And so you're able to see that it works, but perhaps when you're looking at it, you're noticing a couple of things, and that it's not very bright and that the image is upside down. So we'll get to that in a second. So let's start building our own pinhole camera, and then we'll talk about how it works. So what you'll need is an empty Pringles can, a thumbtack so we can make our pinhole, and then you'll need wax paper, and I'll explain why, and you'll need foil, and then you'll need something to cut the Pringles can with, as well as the wax paper. So you can use an X-Acto knife to cut the Pringles can, but I've brought a bread knife, and so please be sure to ask for help when using sharp objects. So to start, we take our Pringles can and we're going to cut about 2 inches from the bottom. And so do that. A little difficult. Adult help may be required. And there's still some Pringle in here, so we're going to dump that out. So, all right, wasn't quite empty. So now you got your 2 pieces. And in the bottom portion, we're going to make our pinhole. So we're going to turn it over, and on the metallic part, we're just going to take our thumbtack, and we're going to put a hole right in the middle. And sometimes you just got to twist it. All right. Now we've got our hole. And so then we need to make a screen. So light's going to pass through this hole, and then we need a screen to project the image onto. And for that, we're going to use the lid. So we'll take the lid, and then we're going to take some wax paper. And you'll need to cut the wax paper to be just a little bit, well, a little bit larger than the lid. So we'll put the wax paper in between this bottom part and the lid. And then we'll need to put the top back on. So to do that, we'll use our tape. Here. And then we'll just tape this guy around here. And so you could take your pinhole camera out like this outside, but you're probably going to get a lot of light coming in through these cracks because your seal's probably not perfect. So that's what we're going to use our foil for. So our foil is going to block any extra light from our pinhole camera. So we just wrap our foil around here. And then we'll tape it up. And before we look through it, I'm going to talk about why the image is upside down and why we need this wax paper as a screen. So let's tape this guy up. We have a completed pinhole camera, which is very exciting. So contain your excitement because we have to talk science now. So let's draw our pinhole camera, which is this Pringles can. And then here's the hole. And here is our screen. And then here is your eye. Oops, okay, so let's say we're going to look at a person. And so let's take one light ray coming off the top of this person, so it correspond to like their head. And this ray is going to come through this pinhole that magically got larger. And the ray is probably going to end up here, and it's not going to end up at your eye. And so that's why we put the wax paper here. We call it a scatterer. And that wax paper takes that light and scatters the light that wouldn't go to your eye into your eye. And so the reason it's upside down is because the ray corresponding to the top of your object is actually backwards. But wait, let's draw the ray coming from the bottom. That might make more sense. So yeah, so now we've got the ray from the feet up here. Draw an upside down stick figure. And the ray from the head up here. And that's why it looks upside down, because the ray that you're looking at is actually crossing here at this pinhole. And the reason we need the wax paper here is so that we can scatter light that might not get to your eye, but we scatter it to your eye. So it's just changing the direction of that ray. Okay, now let's see if we can look through something in our pinhole camera. So I'm going to get a picture of something very bright and colorful and hope that we can see it through the pinhole camera. So the reason that the picture isn't very bright is because the hole's really small. So there isn't a lot of light that's coming through. If you are to make your pinhole bigger, you will be able to see a brighter image, but you won't be able to see as small of features. So you kind of have to find a happy medium. But let's see if we can do this here. So to turn off the lights, do I need to? Okay. Okay, thanks, Cindy. So let's see. It's a bit difficult. Yeah, it might be hard to see something through here just because my phone might not be bright enough. Well, let's see now. Oh, there we go. Okay. Yay. My phone was just too dark. Tilt the can. I always tilt it the wrong way. All right. I won't move. But yeah, so you can see the blue bars on my phone, green one, pink one. That is probably my phone that's coming bright. But yeah, we are looking through the pinhole. We're not looking at my phone. My phone is down here and the camera is right here. Yep, there's the image. Oh my gosh, it's so faint and so small, but it's there. So you will probably have a lot better luck if you take your pinhole camera outside and you go out and look at some stuff. So thank you guys so much for coming to our Laser Fun Day. It was great.
Oh. All right. Thank you, Miriam, so much for that wonderful presentation. Okay, so sadly, this means that Laser Fun Day 2021 is coming to an end. We really hope you all enjoyed the optical demos that you saw today. It's been so exciting for us to plan this event for all of you. Hopefully next year we'll be able to host an in-person event again, but you'll still be able to find us here at laserfunday.org if you can't make it to Tucson.
We hope that you use the Laser Fun Day website as a resource for fun and education. Check out the extra demonstrations that we recorded under the Demo tab and fun optical simulations under the Simulation tab. If you learned something new today and want to share it with us, please reach out to us through our email, laserfunday.ua@gmail.com, or through the website, laserfunday.org. We would love to see any scientists at work or do along constructions that you made throughout the presentations. Feel free to send us photos and possibly be featured on our college's website.
We also want to take a moment to give a huge shout out and thank you to all of the students and faculty who helped us create Laser Fun Day this year. Everyone worked super hard to change this event to a virtual setting, and we could not have done it without you all. So thank you so much, guys.
We are happy to say that the first ever virtual Laser Fun Day is a success. We can't wait to see you all next year. Thank you.